thank you, Lars, the organizers, Alex, also who originally invited me. I'm glad to be the first experimentalist, although it is a little bit intimidating. So let's see how it goes. So I'm going to discuss today thermal and magnetothermal transport in monolayer and bilayer graphene, and I want to emphasize this is work in progress. So I was requested from the organizers and sort of discuss things really from an experimental point of view. What are the challenges in these measurements? And, so I'm really going to approach things from as little theoretical input as possible, in the sense that I want to use some very rudimentary or even crude arguments to motivate us as we go through. So let me start with the team. So we're working at Harvard in Philip Kim's group, and I want to take a second to thank Philip for his long-sighted dedication to these measurements, which are very, very challenging. Artem Talinov is the senior grad student who I've been working with for many years now, and he's been the lead on the zero magnetic field results that I'll show you, and we've been working very closely on the magnetic field results. We've been working many years on refining all of the technical aspects that you're going to see, and if you like that kind of thing, you can read our recent review of scientific instruments article. So our thermal team is growing. We have new members, and I'll only mention some of those things glancingly. And there's an archive preprint where you can read a little bit more about some of the work related there. So let's start. So the essence of this hydrodynamic question is a question of, let's say, transport regimes in condensed matter physics. So the one that we all grew up with.
May I just ask a quick technical question first? Am I the only one seeing a big blue box near your arrow?
My arrow meaning?
So they're just like big blue boxes
mouse
on top of yours. I'm just wondering if it's my technical
problem. I see it too.
Okay, so and there's something weird with the screencast. It kind of blocks out part of your presentation, and yeah.
Where is it now?
A T shape to the right, extending to your arrow.
It follows your pointer.
Yeah. So it works fine, but
I wonder
if you move this is going to get weird, and things are not going to be seen, I'm guessing.
So this is the video, Zoom video or something. Like if I put it here, is it still there?
At the bottom, there's a big blue box. No, it's on the right.
Right.
Well, so likely that is probably that some of these video boxes that opens on the screen. So you just get rid of that. I think that's probably the best.
Here we go. Now it's hidden. Is that
right?
Yeah. Now it's exact. Now it's at the bottom.
All right. Well, looks like Zoom is not as intelligent as we had thought. All right. So good. So right. So electron transport regimes. Now, just keep in mind, I can't see anybody now, and I can't see. I apparently don't get any sort of notification about the audio. So bear with me if you have a question or something. So essentially, it feels like I'm talking to myself. So electron transport regime. So we have our ohmic diffusive regime, very large, often very dirty samples, and there's really sort of a time scale here, in the sense that over the history of physics, the samples became smaller and cleaner. We reached this ballistic regime, right, which was very sort of attractive in the point of view that you can sort of make these nice wave-like calculations of how electrons propagate, or make billiard ball style setups where electrons bounce off sidewalls and so on. And the one that interests us now, which is the more recent realization, originally by apparently Guruji in '62, that if your electron-electron interaction length scale is short enough compared to any other length scale in the problem, then you should reach a regime of hydrodynamic behavior, where your descriptions should become that of slowly evolving conserved quantities. So the context for us today is graphene. Graphene remains this sort of miraculously beautiful material which keeps on bringing new physics, and its core feature being this linear dispersion, And there are several properties it possesses that make it relevant for this search for hydrodynamics, right? So it's low dimensional, which has implications for interactions and for quantum fluctuation. It's clean, so chemically one doesn't tend to get many, sort of chemical disorder sites or structural disorder, and you have these symmetric, these two carbon atoms in the unit cell that help out with that. You have a very small Fermi surface, so umlaut scattering becomes negligible. You have strong interaction. So if you consider that dispersion relation and the dimensionality, and you compare the Coulomb to the kinetic energy scales, you get a constant for any energy that you consider. So there have been, as all of you know, many observations already about this hydrodynamic regime, starting with these negative non-local resistance, superballistic conductance, and more recently imaging experiments. Looking at flow profiles in different geometries. Graphene, of course, is even more special because we can tune our chemical potential to be at some finite Fermi energy up here, and so we can discuss its physics in terms of that of almost like a metal that happens to have a linear dispersion. But we can also, using an electrostatic gate, tune that chemical potential to zero, which is a very special property that doesn't arise in most semiconductors and things like this. This regime is very special, right? Because you've lost entirely this Fermi energy, this scale that is so important when you're considering Fermi liquids. And your carriers in the system are only thermally excited electrons and holes. So there is, in a sense, there's no Fermi surface almost to speak of. But because of this linear dispersion, this object that we're dealing with is actually a relativistic plasma, but that exists at low energy, right? And the only other experimental example of this that I know of, I think, is the quark-gluon plasma that we get by colliding heavy nuclei together in accelerators. And other than that, you have to consider cosmological objects. So this is a really unique opportunity for condensed matter physics, sort of bring in physics from very different contexts in this description, and maybe also find applications for it, which is very special. And there have been observations, starting with this paper from Philip's group of the Wiedemann-Franz violation, and then later on using optical excitation of the quantum critical conductivity, and then imaging from Harvard's group, Harvard group of the quasi-flow at room temperature. So today we're going to concern ourselves with this one. So this Wiedemann-Franz violation, I'll get into what that means in case you need a refresher. It's basically the key feature is this peak in a certain quantity that I'll describe. Okay, and this has to do with thermal transport. So thermal transport, why is that relevant for hydrodynamics as an experimental probe? So I want to sort of make a very basic argument for why it's important. And so we're going to map out how the electrical and thermal properties behave with different types of scattering, when different types of scattering are present in the system. So we start with our sort of baseline, which is elastic impurities scattering. So in this case, we imagine that there's some scattering rate, which we'll call large gamma. So that large gamma randomizes the momentum, let's say perfectly. So let's say that our electrical conductivity, or its inverse, takes up this factor of this large gamma, this impurity scattering timescale. So the same holds true for the energy, right? Our energy will be, let's say, perfectly randomized in some way, and so we'll put that large gamma also in our thermal conductivity. Electron-electron scattering, on the other hand, is different, as you know, because it conserves momentum. Now, if you only have electrons present in that system, then that momentum is one-to-one, so to speak, with the charge current. So if momentum is conserved by the scattering event, so is the charge current. And so, so the electrical conductivity doesn't care that this is present. Now, it's important to mention that the reason that holds is because of the absence of umlaut scattering. On the other hand, for thermal conductivity, the scalar energy can be redistributed by the scattering event So we'll say that the thermal conductivity picks up a factor of this little gamma, this electron-electron scattering rate. So let's take stock, and here is the Wiedemann-Franz law. So if you take the ratio of the thermal conductivity to the electrical conductivity, in normal metals, it turns out to be proportional to the temperature times a set of fundamental constants that together form this Lorentz number, L0 here. So we can ask, in this situation, if we take both of these scattering types into account, how does that change this Lorentz ratio? Does it change it away from the value that you get in a normal metal? So we can construct our Lorentz ratio, which is the Lorentz number for our electron-electron interacting system, to our normal metal value, and we get this, this ratio that depends on the ratio of the electron-electron scattering to the impurity scattering, little gamma over big gamma. So if we have very small amounts of electron-electron scattering in the system, then this number goes to 1, and we're back to the normal metal regime, the sort of Wiedemann-Franz law, so to speak, holds. On the other hand, if we have very strong electron-electron scattering, then this ratio becomes very large, and our Lorentz number is suppressed. So the Wiedemann-Franz law is violated, and it's suppressed in that case. So what happens if we're sitting now at charge neutrality and we have electrons and holes present? In this case, if you apply a voltage bias to the system, what you get are counter-propagating electron and hole pairs. Now, those counter-propagating pairs carry no net momentum, but they do carry charge current. So there's no special conservation there. And so that conductivity will pick up a factor of an electron-hole scattering rate. On the other hand, if you apply a thermal bias in this situation, you generate co-propagating electron-hole pairs. And those co-propagating pairs carry a net momentum and energy, but they don't carry any charge. So in this case, we have that momentum is conserved, and therefore the energy current is actually conserved. And so our thermal conductivity shouldn't pick up this factor. And so in this case, if you compute the Lorentz ratio, you get something that looks a bit different, because now if the electron-hole scattering rate is large, the Wiedemann-Franz law is violated, but it's enhanced. The Lorentz number goes above 1. Surprisingly, this is actually roughly consistent with the results of actual rigorous theory treatments. So to summarize, we have that the Wiedemann-Franz law is violated in the hydrodynamic regime, not necessarily non-Fermi liquid, I should say, but it's in different directions. The Lorentz number is enhanced at charge neutrality, but it's suppressed when we have a single carrier. So if we go back and think, about our graphene situation, the funny thing about the arguments that I just told you is that they didn't invoke at all the linear dispersion relation of graphene. In other words, its most salient and unique property didn't seem to matter, which is very odd, because if you look at the theory works, there's now an extensive number. They do very heavy theoretical lifting to take this into account. So it sort of begs the question, right? Is this actually sort of generic in some sense? And what's amazing is that nature has kind of gifted us a way to check that, because if you make a bilayer graphene stack, so in this case, I mean AB bilayer, Bernal stack bilayer graphene, the spectrum looks like this. We still have a zero bandgap system, but this time it has a mass. So again, we can tune our Fermi energy to be up where we can discuss it in terms of a metal with some effective mass, but we can also tune that Fermi energy to 0. And again, we have the case of this kind of thermal plasma, but this time it's not relativistic. Now it inherits all of the relevant properties for monolayer graphene. It's 2D, it's clean, it has a small Fermi surface, and the interactions this time are, especially at low densities, even stronger, because if you compute the Coulomb to the kinetic energies this time, they diverge as you go to 0 energy. So in fact, you might think interactions might play a stronger role in bilayer graphene than monolayer graphene. And in fact, there is a growing number of theory works that have treated this problem, and indeed it turns out to be in some sense comparable. There are a few distinctions that I'll get to, but roughly sort of similar to what happens in monolayer graphene. And so far there have been observations of the electrical conductivity including this electron hole limited transport and more extensive DC conductivity measurements that came more recently. So this sort of presents a challenge to us, which is, can we measure the thermal transport both at and away from charge neutrality in both of these systems, and see, do they live up to the expectations, and how do they compare?
Could I ask a question on the previous slide?
Yeah. The chart here, this one.
Yeah, this slide. So I'm trying to understand how it comes about that your rates add together, because one is the impurity scattering rate. So this is the rate that degrades momentum. And the other one is the electron-electron or electron-hole scattering rate, which has nothing to do with momentum. And I would have expected these rates to add as inverse in the conductivity, let's say.
Right. So I was a little sneaky there, because I used the inverse conductivities to put those in.
Let me put it differently. Like, for instance, in the conductivity itself, I would have expected something like 1 over gamma EE plus 1 over gamma M with different weights.
Yeah. So you see in the chart I wrote, kappa to the -1 there, or sigma to the -1.
Yep.
Okay. Yeah. So so in other words, this really is the resistivity going as the. Do you mean like in a Mattheson's rule type of?
Yeah, for instance.
Yeah, right.
Yeah.
So yeah, I mean, I think it's true. I mean, this is, let's in all likelihood, this entire slide is probably wrong, right? So I'm trying to sort of motivate the physics with using some very cartoonish arguments. So if you were to do this with Mattheson's rule. But I have to write down how it comes out. But
I'm not sure if that's relevant, but maybe that in the hydrodynamic regime you basically add rates in some cases.
So this has been like worked out in a proper hydrodynamic analysis. This is somewhere in some paper.
Like, I know only one example, but this probably was solved. But basically, if you have a very strong electron-electron scattering, then basically you would average the resistivity and not the conductivity.
Mm.
Yeah, thanks.
What's funny is this Lorentz ratio for the electron-electron case here, like that actually matches up to a couple of papers that I've seen. So it's possible that's actually, even if the argument is incorrect, that it could be the result is somehow capturing something, and maybe there's a reason for that.
Okay, thanks.
Good. So what we want to do then is to measure the thermal transport of these two different systems. So how do we measure thermal conductance? So let me tell you about how our measurement works. So imagine that you have a resistor sitting at a finite temperature. So already for almost 100 years, we've known that there is a thermal noise that arises on that resistor, and the mean square value of that of the voltage fluctuation is proportional to the electronic temperature of that resistor. And so if you take that resistor and you hook it up to an amplifier, which is here this triangle, and you measure the voltage fluctuations over some bandwidth delta F, then you can get a number that's proportional to that electronic temperature. So now if you hook that up also to a source of current here, that's the circles of the eye, then you can drive some current through and perform a steady state measurement. We'll inject some power into that resistor, and that power will have to be balanced by some energy loss. So our power injected is going to be I squared times R, the resistance there of that resistor. And the power out is going to be every possible energy loss mechanism that the resistor possesses. That can be a lot of different things. Hot electrons will accelerate in the applied electric field and gain energy, and they can lose that energy once they reach cold contacts at some back temperature. The electrons can interact with phonons and lose energy to the phonons. Umklapp scattering can contribute to energy loss. You can have inelastic impurity scattering as well, radiative losses. There's really a whole zoo of losses that you can have, and that should be, in a sense, an intuitive idea, because if you've ever seen a light bulb, or perhaps older light bulbs, you know that they give off the light that you want them to give off, but they also give off heat, right? So every time that you drive these currents, you're losing energy in many different ways. And which ways you lose depends very much on the details of the system. But what happens if that resistor is a piece of graphene? This is where yet another amazing property of graphene, it turns out that there's a large temperature range where actually electronic diffusion determines entirely the energy loss. In other words, the electrons gain energy by accelerating in this electric field, and they lose it only once they exit the graphene and head off into this bulk metal, which is thermalized at some cold temperature. And so those electrons, those will have some bulk thermal conductance value, and whatever the temperature changes that they're experiencing in the steady state condition will have to balance the injected power. So what that means is you can extract out a thermal conductance value, which is just the ratio of your injected power to the measured temperature rise. So here's an example of what that looks like. If you measure this thermal conductance as a function of the bath temperature, then what you can see is that up to a temperature of about 100 Kelvin, the extracted thermal conductance goes as the Wiedemann-Franz expectation, which means that it's governed entirely by electronic diffusion. And that's as far as I know that's unique to graphene. Now, above that temperature, you see that this power law kicks in, and this power law, which is about T to the fourth, has to do with electron phonon energy loss. Now, if you look at this, you might say, well, if I'm losing energy to phonons, why is my thermal conductance going up, right? Shouldn't it actually go down? So that's because this measurement is strictly speaking only of thermal conductance as long as you're in that electronic diffusion regime. Once you're out of that regime, what you're really measuring is the sort of total amount of energy loss. So I bring that up because that'll come up again. So let's, so obviously if the measurement was that simple, you'd have seen a lot more papers out by now. But there's a lot of technical background. So let me just give you a quick glimpse. So this is what an actual sample looks like. So we've got over here, there's a microfabricated sample here sitting on this chip, and it's connected to this matching circuit, which is some arrangement of inductors and capacitors that we choose in order to better couple those high frequency noise fluctuations from the sample to our amplification circuit. And we've refined that quite a bit, and we've gotten bandwidth greater than 100 megahertz, and we work in frequency ranges of from 100 megahertz to a gigahertz, and we have roughly half millikelvin precision with reasonable averaging times. And we've done this now in actually several different systems. So, this very compact cryo cooler, we have this in the middle here, the sample in vapor variable temperature insert, which has a magnetic field and some lower temperature. And then on the right is a dilution refrigerator, which goes to sub-Kelvin, sort of millikelvin range, or tens or 100 millikelvin range with a magnetic field. So, when you have to do this over many different systems, you learn a lot about the details of how it works. So we've really refined this technically quite a bit. And the data that you're going to see today comes from these two systems on the left here. So let's look at some data. So here is an actual device. This is a rectangular patch of bilayer graphene encapsulated in hexagonal boron nitride. That's also a 2D material. Here we get it in flakes, and it's a very good clean insulator that we use to keep that graphene away from the disorder that exists on the substrate, keep it nice and flat, and so on. So first, we measure the electrical resistance. So here's the electrical resistance of this patch of bilayer graphene as a function of the density. So there's this peak at 0 density, and that corresponds to when our chemical potential is tuned to the Dirac point, or as close to the Dirac point as the disorder will allow us to reach. And as that density increases and our chemical potential goes up through the spectrum and our density grows, that resistance goes down. So here's the thermal conductance, and you see that the thermal conductance in this case has sort of a global minimum near that zero density, and then increases as the density goes up, right? And you might expect that from this resistance plot, right? If you were thinking in terms of the Wiedemann-Franz law. So we can quantify that by computing our Lorentz ratio, and here's what that looks like. So at zero density, the Lorentz ratio has this small peak, and then dips at some low density and sort of flattens out again. So since we're chasing after hydrodynamic phenomena, we know that disorder should play a very important role. And in this sample, it's not shown in the picture, but there's an oxide that's grown on top of it in order to deposit a metallic gate on top of this. It turns out that process actually induces some kind of disorder in the sample, in addition to the fact that on the bottom, there's an oxide that's sitting there at some distance that also causes disorder. It turns out that recently there was a way discovered to mitigate that very dramatically by using graphite gates. So here the idea is that your graphene sits inside these layered insulators, and then inside that, in this growing sandwich, you have two flakes of graphite of some thickness. It turns out that graphite is essentially an atomically flat metal that serves as an extremely clean gate electrode, which also helps to screen away any kind of disorder that might exist in the environment around. So let me show you then the same data that's coming from this device. Here's what that
Jonah,
looks like. Yeah.
Sorry, could I ask you a question? There's something very basic I don't understand.
Please, please.
If it seems that if the sample is in the hydrodynamic regime, then shouldn't the thermal conductivity grow near charge neutrality? Because you have this basically ballistic heat transport, right? And in your case, it decreases.
Right. So the actual value is going to depend on sort of the details like geometry and the temperature that you're sitting at and so on. So that's why we'll tend to quantify it using the Lorentz ratio. In other words, for the same sample with the same point and parameter space, how much is it thermally conducting compared to that resistance.
But so is the sample qualitatively different from a single layer graphene? So in earlier experiments, Krosno, Philip Kim, and also in Subir's theoretical work, right? The thermal conductance should actually have a peak near charge neutrality. And here the middle graph shows seemingly the opposite.
You're talking about just the red curve, right?
Just the red curve for thermal conductance kappa in the middle.
Right. So this sample it turns out is relatively disordered. So whether this peak shows up, it depends on how clean. So let me say something that maybe was buried here, which is that the effective disorder in these zero bandgap systems is that when you're very close to charge neutrality, your chemical potential is not actually sitting at the Dirac point. It's actually in a charged puddle regime. In other words, you have a background potential, and at any point in space, what you have is some small doping. And so what you measure is sort of an average over these electron-hole pockets, right? So so if you sort of imagine your electrochemical potential is fixed in space, and your spectrum is at locally the density is being modulated. Okay, so what you really measure is an average, sort of disorder average over many points, only some of which are truly at charge neutrality, and other ones which aren't. So this is why it's so important to be clean.
Thank you. But still, is it fair to assume that the electron-electron mean free path is shorter than the size of these puddles, or is it not clear?
It's smaller in the size of the puddle. Okay, so the puddle is in a sense.
Well, is the disorder long range or short range point like impurities? Okay,
that's I don't know, a trickier question that I don't want to nail myself to the wall with the wrong answer. But I think that's a question that we can try to answer with some of the things that we measure. In terms of the mean free path, I think that the charged puddle is in a sense put a bound on that mean free path, if you will. Even though those, so the sort of length scale of modulation of that potential is not necessarily coincident with what the mean free path would be, but that's sort of a rough guess.
Okay, thank you.
Of course, mean free path, just to say, right, is a function of density, right? Because you're screening of order changes and so on, and that'll come up later in the talk also. But yeah, it's a good question, right? Because so really, you should think of this sample, this data, as being from a relatively disordered device, right? So here is the clean case where what you were expecting, really happens, in the sense that, so in the electrical properties, we have a higher resistance, right? So as I was saying with those charge puddles, right? If you reduce, or if you want to think about it, growing the size of the charge puddles, right? Then you can get closer, so to speak, to that Dirac point, right? So if you look at the distribution of, in your sample, the number of points that are truly at the Dirac point, more of them will really be there. So your resistance will actually grow. Is one way to think about it. So meanwhile, the thermal conductance.
And could you repeat what the difference between the red and blue curve is? Is it adding graphene as a screen there?
Yeah, exactly. Yeah, it's graphite, but yes, it's using graphite as a screening layer and the gate. Yeah.
Thank you.
So the sort of residual density here is roughly an order of magnitude smaller. So so roughly speaking, you can say that the charge puddle size is roughly order of magnitude larger in the clean case. So the kappa, right, looks very different, right? So as you were expecting, it has this peak at zero density, right? And then it has a very strong suppression, and it comes up again. And the Lorentz number inherits that. So we have this very sharp peak at zero density, these very large dips, and the value starts to come up. So clearly there's a very large difference between the sort of what I've called the dirty case and the clean case. So let's look at what happens when we vary the temperature. So here's the dirty case. So here's our dirty sample, and we start to we raise the temperature, and you see that at charge neutrality, the Lorentz number increases, right? And it turns out that there's some theory. Here I'm taking as an example from Zorania et al. Recent theory on a bilayer graphene, where you see this kind of, at least qualitatively, that behavior, that the Lorentz number at zero density should increase with temperature. And closer in, you see similarly, you have these little dips, and then this sort of flattening out. So that's reasonably in agreement with our expectation, even though this sample, right, is more disordered. So what happens in the clean case? So here's that clean sample, and at charge neutrality, you see that there is again that rising value of Lorentz number at zero density, even though the values actually are lower than in the dirty case. Meanwhile, there's a much more dramatic suppression which survives higher temperature, but at lower temperatures there's actually this dramatic enhancement here in the Lorentz number. Now that should be quite surprising, and it is, and so I want to address that, because one of the things the organizers asked from me is to really, to give that look at, the sort of how the sausage is made, right? So, what are the in other words, what are the experimental artifacts that can come up? And we're going to take, a look at that. So let's take our what we call the self-heating measurement, and consider what happens if you have a contact resistance, right? So we don't just have graphene and these perfectly thermalized leads. Really, things aren't so perfect. We have graphene connected to these metal leads that we have to fabricate and evaporate, and there are ways in which one can get a resistance at the interface between the graphene and the metal. So if you take these steady state equations and you ask, well, how does it look when you have that contact resistance? Your thermal conductance, which is the ratio of the applied joule power to the measured temperature rise, looks a little bit different, because the resistance in your joule power includes both the resistance of the graphene channel and the contact resistance of the graphene. On the other hand, the temperature rise you measure is actually only of the graphene, and that's because those metal leads are very, very strong electron-phonon coupled, bulk compared to the graphene, metals, which are very well thermalized to the bath. And so, in a sense, there's only some proportion of your applied joule power heats up the channel, but the entire resistance, including the conductor resistance, is going into the power, right? So what that means is this ratio will increase. So, to show you what happens in a very extreme case, if you take a piece of graphene and you put it in a perpendicular magnetic field and you drive it deep into the quantum Hall regime, then you can really make this extreme, because in that case, if you're sitting at a quantum Hall plateau, then your graphene sample is entirely ballistic. The bulk is gapped, and you only have transport by ballistic edge states. So there should be actually no voltage drop whatsoever in the graphene channel, and only a voltage drop at the contacts. And what happens to this kind of measurement? You can see here the blue dots are effectively like the signal strength, and you see that signal strength in the region of this nu=2 plateau has vanished, and the corresponding Lorentz number has exploded. It's higher than 100. It's several hundred, almost 1,000 at some points, right? Now that isn't physical, right? Because the thermal conductance of electronic edge states has been measured in a few systems, including graphene, and it's known that these edge states carry a quantum of thermal conductance, right? So if you have nu=2, you should have 2 thermal conductance quanta, right? So this is an artifact, right, of the fact that our voltage drop is actually no longer happening in the graphene channel. Now, we're not in the quantum Hall regime, right? We're in let's say B=0. So what happens in B=0? To give you a feeling for what that looks like, this is some data from Shah-Leilani's group, where they measured the local voltage in 2-terminal graphene devices, and you can see on the left is the case where you're sitting right at the Dirac point. There's a diffusive linear voltage drop throughout the channel, whereas at very high density in a clean enough device, the sample eventually becomes ballistic. There's very little voltage drop through the channel, and there's most of the voltage drop at the contacts. Okay, so this is relevant even if you have a clean enough device at high enough density. This is something that we have to worry about. And in fact, if you compare that measurement to a measurement of the mean free path in sort of comparable devices, you'll see it looks very similar, in the sense that as the mean free path grows at low temperature and high density, that's where we see that the apparent thermal conductance and Lorentz number are exploding. In other words, we have to be careful in very clean devices at high density.
Sorry, can I ask one small thing? So can you repeat again how the temperature of graphene is measured, actually?
So what we do is Johnson noise thermometry. So we're measuring the high frequency fluctuations of the voltage over some large bandwidth that we fix, and we have a calibration process to back out the temperature from that.
Yeah, but your temperature changes, right? So it will be different, close to this voltage source, and graphene would have a different temperature, right? So there is a temperature variation across the system, right?
Yes, that's right. That's right. So what we have to take into account is the temperature distribution in the graphene, right? So if you assume a uniform thermal conductivity, you assume that your contacts are sitting at the bath temperature, then you can write a very simple one-dimensional heat equation and solve for the temperature distribution. So it turns out that the Johnson noise measurement measures an average over that distribution, and that turns out to be a numerical factor.
Thank you very much.
Yeah. Good. Okay, so let me, as an aside, one solution to this problem I'll just mention, right? So the sort of heart of the issue here is that we're trying to do thermometry on the same system that we want to sort of measure and learn about, right? So one solution is to separate that, have your thermometry, right, be separate from the system that you're usually measuring. That's usually the case if you look at people who do bulk, measurement of thermal conductance. So this has been a large focus of my work in Philip's group, has been developing a way to separate our thermometry and our system of interest by using what we call non-local noise thermometry. And so what we do here is we take advantage of all the wonderful properties of graphene for thermometry, and we keep our graphene thermometers in the diffusive regimes at all times, while a bridge between two thermometers, can change state. And a natural evolution of this is that we can do it now for different materials. So we took this to the extreme and we connected two graphene thermometers with the carbon nanotube. So there's interesting hints of some one-dimensional phenomena, and you can see that in our recent preprint. But does this have any consequences for our graphene discussion? And there's some hint that it does. So here's some data where we took such a device made of monolayer graphene. So you can see here on the top is a Dirac peak in the resistance. Then in the middle is the thermal conductance, which shows that global minimum position there at the Dirac peak. And the Lorentz ratio here at the bottom, at low temperatures at 5 Kelvin, you can see that it's a roughly gate independent value of 1, right? So that's the impurity dominated regime. And as the temperature goes up, we see this suppression at low densities, which then flattens out, even to relatively high densities. So this is I think a hint that we can reach this regime using this new method. But that'll be stuff that we hope to discuss in the future. So for now, let's get back to our devices. So since we're trying to do a sort of a look at as an experimentalist what you have to watch out for, right? So there are single particle effects that can mimic some of our expectations for hydrodynamics. So it's always important to go through and check what those could do. So in one of the dramatic signatures here is that suppression. So let's say we discount what's happening at high densities, low temperatures. In other words, anytime that this Lorentz number is rising in this uncontrollable way, we can just ignore it for the time being and instead look at where the Lorentz number is suppressed. That suppression is not accounted for by the stuff I just told you, and the minimum Lorentz ratio that we get there is 0.04, which is among the lowest you can find, if not the lowest that you can find in the literature. So one question is, can anything mimic this suppression of Lorentz ratio? And there are some things that can. So the first thing that can is electron phonon scattering at low temperature. So at temperatures below the Bloch-Grunweissen temperature, electron phonon scattering becomes inelastic. And so in other words, it degrades the energy current that you can get. And it turns out that this Bloch-Grunweissen temperature scale is proportional to the Fermi wave vector. And as we know, the Fermi wave vector in graphene is relatively small. So that means that this Bloch-Grunweissen temperature is quite small. And in fact, we observe our suppression beginning far above the Bloch-Grunweissen temperature, roughly a factor of 10 above. So we think that this is, we're comfortable saying that this is not accounted for by electron phonon scattering at low temperatures. There's another effect to take into account, which is that when electrons are in the non-degenerate regime, all right, for T greater than TF, you can have a reduction of Lorentz ratio of about 25%. Obviously, 25% can't account for everything we measure, so that's clearly not the full explanation. Whether that's actually contributing, we would have to compare to high density data to really be sure about that. But for certain, we can say that for Lorentz suppressions of this magnitude, it can't be either of these two effects. Meanwhile, at charge neutrality, there's another effect that one should think about, which is something called bipolar diffusion. A simple way to think about that is that if you're sitting at charge neutrality, the thermoelectric voltage, right, of the two species, the electrons and holes, is perfectly canceled. And so it turns out that this leads to a local enhancement of the Lorentz ratio. This turns out to be very weakly temperature dependent and quite small. And so even for these sort of moderate Lorentz numbers here at charge neutrality, this can't account for it, and certainly can't account for this temperature dependence. So this is the story so far that we have. Let's try to summarize that. So in bilayer graphene, we observe that at charge neutrality, we have a temperature dependence of the Lorentz ratio that is roughly comparable to theoretical expectation, but the magnitude is smaller actually in our cleaner case, which we don't yet understand. At finite densities, there's a large Lorentz suppression, and that is for now and which shows up in our cleanest device, which is our best evidence for a strong hydrodynamic regime that's rising at that low density. At higher densities, we have to do more work to find out what's going on. So with these sort of preliminary conclusions in mind, let's go back and look at monolayer graphene. So here, we're going to take an encapsulated monolayer graphene device with a piece of graphite there beneath as our cleaning gate. And let's jump straight to the Lorentz ratio. So again, we have that near zero density. There's this sharp peak. There's two suppressions happening next to it, and then this uncontrolled rise that's happening at higher density. So since we've already learned that we should be skeptical of this large number here at higher density, well, let's zoom in to the relevant density range, which is over here. So first, the suppression that we observe is about now 0.25, right? It's not as strong as it was before, but it's strong enough that we can say that this should be of hydrodynamic origin. Now, the temperature dependence at charge neutrality now looks quite different, right? In this case, you see that at low temperature, which is the black curve, the lowest temperature, it goes up, it reaches some maximum, and then actually comes down again, right? Now, that's comparable to what people have sometimes called the hydrodynamic window that exists in monolayer graphene. And this was what was observed in the 2016 work. Here it happens because we have the impurity-dominated regime at lower temperatures, and there's a specific phonon branch that causes energy loss at some higher temperatures that doesn't come up in bilayer graphene by chance. So they have quite different temperature dependence at charge neutrality. But now this temperature dependence is sort of consistent with what was observed, but again, that value is actually smaller. It's not quite as dramatic as that 20 that was observed before. So our conclusions look a little bit similar in the sense for monolayer graphene, in the sense that at charge neutrality, we have a temperature dependence of the Lorentz ratio that's comparable to theoretical expectation, but the magnitude is not quite as large. While at finite density, we do observe the Lorentz suppression, right? So there's sort of this funny situation where we can say that there's definitely hydrodynamic effects coming in, and yet at charge neutrality, they're not quite as strong or dramatic, let's say, as we might have expected. So you know, for me as an experimentalist, this begs the question: well, okay, can we look at this in any different way, right? Is there something happening here that has to do with the way that we're measuring that could be affecting this, or so that we could measure in some different way and get some independent information? So this is why we came to magnetothermal transport. In magneto transport, let's say if you look at a Drude model, right, you have that the electrical conductivity is modified by this number that depends on the cyclotron frequency times some momentum relaxing time scale. And so you can sort of phenomenologically say that the same thing will happen with thermal conductivity, except that it'll involve an energy relaxing time scale. And this has actually been done for several decades to account for the behavior of many bulk materials, including metals and semi-metals, even up to works quite recently. You know, so sort of phenomenologically it worked. But to give us a little bit more of a solid footing, let me invoke theory once. And so here is some work from Lucas and DeSarma, Andy Lucas, where they computed these coefficients in a hydrodynamic regime, and they found that the longitudinal electrical conductivity depends on that big gamma, the impurity gamma, while the thermal conductivity depends on big gamma and small gamma. In other words, the electrical conductivity takes the impurity scattering, while the thermal conductivity takes the impurity and the electron-electron scattering, right? So this is, you know, sort of, in some sense, evoking those rudimentary arguments that I was showing you. So by using a magnetic field, we might be able to get some independent insight into what these numbers look like, the comparative magnitudes, let's say, of the impurity and the electron-electron scattering lengths or rates. So let's try this in our bilayer graphene sample. So we compute the sort of traditional magneto resistance value, which is the value at some finite field, subtract the zero field value and normalize to the zero field value. And what we see are these nice parabolas as long as you measure over a small enough field range. And we can construct the same quantity for our thermal resistance. And this is what we saw. So we get nice, reasonably nice parabolas, but you can see they're going with the opposite sign, right? So this was very surprising. So let's take a look at this a little bit closer. We'll fit our parabolas using some coefficient here. So I'm going to call this the electrical curvature and the thermal curvature. And here's a plot of those curvatures versus density. So the electrical curvature is positive for all of these densities with the sort of a gentle peak around zero density, while the thermal curvature has this sharp negative peak that happens at zero density. And if we vary the temperature, that negative peak is deepest and narrowest at lower temperature, and it sort of becomes more shallow and wider as the temperature goes up. So what about in monolayer? So we did the same thing in our monolayer device, and the behavior there was somewhat more complex at low temperature, but roughly comparable in the sense that for some higher temperatures, we have a positive electrical curvature, and then this large negative peak in the thermal curvature close to zero density, which is even larger than in the bilayer case. So to consider where this might be coming from, the first thing one should really do is look at the thermoelectric transport matrix and take into all of the off-diagonal components into account and look at how this rectangular boundary condition is affecting that when you put the magnetic field on. But since I'm trying to keep as far away from mathematical arguments as I can, I want to give more of a physical motivation for what we're going to look at. So the off-diagonal components that I'm talking about here, the first one that one might think of is the Hall voltage, right? So every time you apply a magnetic field to a 2D system, Hall voltage arises, right? And that Hall voltage is important because it modifies the current distribution in that sample. And that's important because we saw that the current distribution is actually important for determining this final number that we pull out of our measurement, right? So that certainly could be playing a role. The reason that I'm personally not convinced by it is that the Hall voltage is asymmetric in density. In other words, it crosses zero at zero density, and so it should vanish exactly where we see the strongest effect, right? So this leads one to think, well, are there other off-diagonal thermoelectric response coefficients? And the answer is yes, there's one called the Nernst coefficient, right? So the Nernst coefficient has actually been measured in graphene, and it's peaked at zero density, okay? Let me just remind you what the Nernst coefficient is if you haven't thought about this in a while. So the Nernst coefficient is if you take a sample and you apply a thermal gradient, so we keep one cold end at T and another hot end at T plus delta T. So if we're sitting at charge neutrality in our graphene or some other system, we're going to generate these thermal electron-hole pairs, and those will diffuse out to the cold end. Now, if we apply a magnetic field, then those diffusion paths will be deflected. And as a result, they'll build up a transverse voltage. And so the Nernst coefficient is the ratio of that transverse voltage to the applied temperature gradient. And actually, over going back several decades, it's known that semi-metals and other sort of compensated or systems that have the presence of both electrons and holes often have anomalously large Nernst responses, and this holds true also for graphene at zero density where it's peaked. So the question that we had is is there a thermal consequence of these off-diagonal responses in a magnetic field? And there is a very sort of sharp way to check that, which is get rid of the boundaries, right? So we can use a Corbino geometry where we have a hot end and a cold end, let's say, but there is no lateral geometry. In this case, the boundary condition is different. So here our electrons and holes, our thermal electrons and holes will circulate around this ring, but they never generate a transverse voltage, right? And indeed, if you go through the math of the thermoelectric response matrix, you'll see that it's the Corbino geometry is really the one that gives you the right answer in terms of getting out the longitudinal thermal conductivity. So we went ahead and made graphene Corbinos. So here's an example of a monolayer graphene Corbino encapsulated in hexagonal boron nitride again. All right, and here's what the thermal curvature looks like. So the rectangular one is this purple curve, which you see has that strong negative peak. And this orange curve is the Corbino data, and you see that that's positive throughout that temperature range. So if we zoom in on that, here are the electrical and thermal curvatures in that Corbino device. They're positive for the entire temperature range. The electrical one shows some very weak small modulation. The thermal one, on the other hand, has this kind of a suppression happening close to zero density. And we've seen this already in a second device that for this particular temperature, it stays positive, and there's a suppression in the thermal curvature compared to the electrical curvature. So, tentatively, we can say that our removing the edges eliminated that negative magnetothermal resistance. So we say, great, we can try to learn something from these Corbino devices. So let's vary the temperature now. So here's the electrical curvature in this device as a function of temperature, where you can see that curvature is increasing as the temperature goes down, right? That's reasonably consistent with kind of a crude style of thinking. But here's the thermal curvature. Now say, Jonah, you fooled us. This actually becomes negative. But this one is becoming negative in a very different way, because before in the rectangular device, we saw that it was peaked very strongly at zero density. But here we see this kind of a butterfly, right? We have that it's becoming more rapidly negative at higher density. So one question is then, all right, what can be leading? Right now, we know that the Corbino geometry should be the right one to pull out longitudinal thermal conductivity. So why should that one become negative, right? In this case, so let me invoke phonons to make an argument why that should be the case. So if we consider that some thermal electron has this path length to travel in our device at zero magnetic field, when the field turns on and that electron path is deflected, the path length increases, all right, in that field. Meanwhile, there's an electron phonon interaction length, which tells you, over the typical length over which an electron will lose energy to a phonon. And we can assume that quantity is independent of or insensitive to the magnetic field. In other words, when we increase the field, the ratio of our typical path length to the electron phonon length increases, right? So we can actually we have a probability of losing more energy to phonons when we turn on the field, right? And that means more energy loss. And when there's more energy loss, as we saw in a rectangular device, that means the sort of extracted thermal resistance decreases. In other words, there is a negative magnetothermal resistance contribution from the electron phonons. And then indeed, if we take our two devices that have two different channel lengths and we sort of estimate a crossover temperature by looking at where those wings are sort of more or less flat. So for the shorter device, that turns out to be a higher temperature than the longer device in a proportion that's roughly in agreement with the channel length. So we think that this is coming out from a phonon effect at higher temperature. So let's now sit at charge neutrality and vary the temperature and see what that looks like, since that's sort of one of the interesting places to look. Here's zero density or close to zero density. We vary the temperature, and these are the electrical and thermal curvatures from one of those Corbino devices. So the electrical signal, is pretty insensitive to temperature until it starts to increase at some low temperature and perhaps hits a peak. Now the electrical conductivity or resistivity of graphene is not so different versus temperature close to the Dirac peak, in the sense that it goes up at some temperature, has a weak kind of a peak, and then kind of flattens out, and that's when you've hit sort of impurity or the charged puddle dominated regime. The thermal curvature, meanwhile, at high temperatures starts out weakly negative, has this shallow increase, and then increases a bit sharper over here. Now, eventually, we expect that there should be some impurity dominated regime. Now, if we map this out, right, so out here, we expect that there's some electron phonon energy loss that may be determining the value of that thermal curvature, right? So at very low temperatures, we expect that there's an impurity dominated regime where the thermal and the electrical curvatures should become connected to each other, right, through the Wiedemann-Franz law, for instance. So there's a question then, is there a hydrodynamic window, since this is monolayer graphene, is there a hydrodynamic window where this thermal curvature can tell us something about that Dirac fluid. So with that, let me, just about out of time, so let me start with some sort of quote unquote conclusion. So we have a set of results here, so we have a large Lorentz ratio suppression at low density in both bilayer and monolayer graphene, and we believe we've ruled out alternative explanations and that this is coming from hydrodynamics. At charge neutrality, the behavior is consistent with what one expects from the temperature dependence, but the values are not quite as large. And meanwhile, we have these magnetothermal transport signatures. It's negative in rectangular devices and Corbino devices where it should be positive, below some temperature scale, and it has a suppression around charge neutrality. There's a lot of open questions that we have. So I just want to leave these here to sort of hope to get the brain juices flowing, right? So what happens at high density, right? That's a question that we can't answer yet, or that we'll be able to do in the future, right? So why is the Wiedemann-Franz violation weaker than expected? Is that just because there's disorder, or is there something else like a difference in the electron-electron and the electron-hole scattering rates, for instance, because of screening or some other effect? The magnetothermal transfer that we observe, is that of a physical origin? For instance, right, if at charge neutrality, if you think of separating your electron hole populations or just modifying the angles at which they interact, does that modify the electron hole friction, right, in some way, or is this just an experimental artifact? And in the Corbino devices, what quantity can we physically associate with that curvature? Is it a scattering time or mobility or viscosity? And is that the same at neutrality versus finite density? What do we learn in these different regimes? And so as an experimentalist, we have a long wish list of things to do. We need to make bilayer Corbinos. We go to lower temperatures to reach the impurity dominated regime, make clean Corbinos to push us much deeper into the hydrodynamic regime and see how that affects our results. There's some multi-terminal measurements of the electrical quantities to do those more accurately. And we have our new method, which can hopefully help us answer the question of high densities. And so with that, let me thank you for your attention. And thanks for the chance to talk.
Thank you, Jonah, for sharing these exciting results with us, and also for letting us in on difficulties that you run across. So there have been a number of questions, but I'm pretty sure there's more. So please speak up.
I can't get to the videos now. Now I don't know how to get to the. Does anybody know if there's a shortcut for me to bring up the?
You want to see? I think you have to unshare the screen. I think.
All right, let me do that, and we'll share it again if we need.
So, are there any questions? Maybe let me ask one. So, I was wondering when you discuss, for instance, the monolayer, how far are you from what you would call Fermi liquid regime? Like I didn't convert the numbers on the spot, but like at some point you would probably expect to recover the Lorentz ratio to be 1.
Right.
Like because you were referring to higher densities and the suppression, but eventually you would probably expect it to come up to 1 again. Like
right. So you could see in the dirty device or dirtier device, you could see that the Lorentz ratio flattened out, and over a wide temperature range, it was really sticking at some value. The problem there in that device is that value was a little bit above 1. So that's to us that suggests that there's actually some experimental artifact there. There's possibly contact resistance contribution, because even if you're diffusive, that can play a role. So this is why I think for high densities, you really have to use this new method, because then we can eliminate these things which are important. Right? So the problem with high density is that that's where your graphene channel becomes most conductive. And so contact resistance, even if it's diffusive, it's going to play a role, and that's going to mess with our numbers. So this is why we think the new method should hopefully get us out of that conundrum and answer this question. Now, the data that I showed you from the new method, this very early data, it does show a suppression that it's saturated at a suppressed value. So I can't make any hard conclusions yet whether it truly returns to the Fermi liquid regime without, sort of, if the interactions can screened out or whatever it is. But I think that that's an interesting open question for us.
Okay. So who else has questions?
I do have a quick one for Jonah, if I may. So you mentioned briefly these transversal responses for Nernst, for instance. So do you have some results for it, and also for transversal thermal conductivity, so kappa XY? So have you looked at those?
You mean like measuring those quantities?
Yes.
So we haven't measured those now, but you can. There are some measurements of that. If you go back, I can send you the references, but it's been measured. The Nernst effect has been measured in graphene by 3 different.
Yeah, groups. I saw it in a slide, but I felt that maybe whether those measurements are being thought of in the hydrodynamic regime or more in diffusive regime, and whether you have a perspective with your technique and samples now.
That's a great question. I mean, I think that so I mean, the short answer is no. We haven't made those measurements yet, but I think we could. So that's definitely going to be future work. So transverse responses are going to be is a big technical challenge, because it means more of these graphene thermometers, and it's not an elaborate setup, but it's something that we hope to do.
Okay. Thanks.
Okay. Who else has questions? Well, I mean, if there's no more immediate questions, let me thank Jonah again for this really nice talk. Yeah, and I guess there'll be probably more interesting results also next week on the March meeting. And the next talk in the series will be essentially the week after the March meeting. So yeah, thank you all for joining, and see you around. Bye.
Thanks everybody.